Hello everyone, my name is Andreas Hellander. I'm the Chief Scientific Officer of Scaleout and I'm also an Associate Professor at Uppsala University. In this presentation, I'd like to introduce three challenges that federated learning faces as a technology. And then in particular, I'd like to talk about how these sort of challenges are driving our development of FEDn, which is our open source project for federated learning. As you know, the key promise of federated learning is the possibility to come together and jointly train a machine learning model that performs on par with or even better than the best possible model that you could theoretically obtain if you were able to pool all the data. In particularly, you can see that the performance of the federated model is on par with the centralized global model, which was constructed by pooling all the data in a central location and training the same network in the usual manner. This brings me to the first challenge that I wanted to talk about today, and that is the problem of statistical heterogeneity, or feature if you wish. So in the previous slide, we had taken the pooled dataset from a dataset called C for 10. It's a 10-class classification problem, and then created partitions that were identically distributed. But in reality, for a FedML situation, you can expect that the data is not identically distributed. And this causes then data heterogeneity or statistical heterogeneity across the alliance. This can, of course, affect convergence of training. So in this figure here, what you see is a pathological situation we created, and this is a typical way to study this problem, where we let each member see only a subset of the available classes in the data. And as you can see, in the blue curve there, if each member only sees 3 of the classes in the dataset, the accuracy of the training can be severely affected. And as the number of classes that each client is aware of increases, so does the accuracy and convergence rate. So this is a highly interesting problem that is worked a lot on in the academic community. There are different ways proposed to tackle this. So one of them is to leverage a small amount of shared data and use various types of data augmentation. And there's a nice overview article that you can read about that linked on the slide. The second challenge that I wanted to bring up is that of system heterogeneity. So if you think about a federated alliance with lots of different members, each training on their own local sites, it's kind of clear that there will be a large variation in both client update speed and system and hardware heterogeneity. And this causes a problem that is commonly referred to as the problem of stragglers. So the problem is follows. If we sort of in a training round, we want each member to update and train about the same amount, and then synchronize, and then aggregate the model, and then this round repeats. But since clients will not finish at the same time, we sort of have to choose if we wait for clients that are falling behind to synchronize, or if we let these clients then update the model even if their update is late. In principle, say that if you're at round K, you request a model from some clients, but then some clients only propose the stat model update at around in the future K plus n, where n is a number greater than 1. So this too can cause various types of problems with convergence, with accuracy. There are some possible approaches to this that has been suggested in other implementations and literature, and that, for example, the most obvious one is to drop clients that do not meet a certain deadline for that round. Another one that is trivial is, of course, to allow delayed updates, but there are also more sophisticated approaches like modifying the objective function so that you, for example, penalizes updates that take the weights too far from their current state. This figure here is an illustration. It's from a recent master thesis conducted by a great student of mine, Jerong Yang. And this is also based on the C410 dataset. So what you see in this figure are experiments, how the accuracy and the number of rounds to reach that accuracy is affected by two set parameters. One is the proportion of clients that are updating late, and the other is how many rounds behind they fall, ranging from 0 to 30. And as you can see, for very hard or high amounts of stragglers, you can see both an effect in the best possible accuracy that you can obtain. But then for a realistic amount of stragglers, typically you will still arrive in our experiments at about the same accuracy, but the number of rounds until you reach that accuracy goes up quite a bit. So this is a problem that is of practical importance for an implementation that you need to think about. This brings me to one of the key points that I wanted to make today, and that is that federated machine learning is not the same thing as distributed machine learning. I mean, sure, they are very similar at a glance. They share a lot of the computational properties, but these two challenges of statistical heterogeneity and system heterogeneity is a clear differentiator. So in a typical distributed machine learning setting, the goal is to leverage high performance data and computational resources in parallel to train a model faster. But typically you start out with a data set that you control, a pool data set. So you have full control over the partitions you make, how you partition the data, how you spread computations across the cluster. So this means that you can ensure that you have good distribution of labels in the data, for example. You can assure that you have load balancing, so forth. So none of this is true in federated learning. In fact, by construction, we have limited or no control of these aspects of the problem. So the challenge then in federated learning is to construct algorithms that make learning robust and efficient in this setting. The third challenge I wanted to touch upon is that of scalability. So obviously it's very important that a federated learning solution is highly scalable. So the schemes that are most common in literature and that we have discussed up to this point, they kind of rely on a central server that orchestrates training and aggregation for capital N clients, and capital N here can be a very large number. This is fundamentally a client-server problem. Of course, it's possible to implement these type of schemes like federated averaging in different ways. In FEDn, our solution, we work with a publisher-subscriber pattern for a lot of the parts of the communication. We use gRPC and RPC for some other things. But here there are many different opportunities to use different types of libraries, different types of tools. No matter what you do, there are some common challenges, and one of them is that you might face weak connections. So clients have weak connections, and this will lead to communication bottlenecks. It can lead to clients dropping out. This leads to the problems of stragglers, which hurt scalability, as we saw. Large model updates. So if you think about the cross-silo case, in contrast to cross-device case, you can expect that you can actually train quite large models on the local sites. Moving these to a central server can become a scalability bottleneck. And in the same setting, so that the orchestrator or central server that aggregates the models become a critical point in the system. It can also become a bottleneck if its performance is not up to the current load. In the rest of the talk, I'd like to talk about how we are designing our solution FEDn, give a high-level overview of the computational model that we are supporting, and a little bit about the implementation choices that we have made. This slide illustrates the high-level model of federated learning that we support in FEDn. So we have organized our solution around three principal layers, if you wish. So we have one layer with clients. So these are the private members that train local models. We have one layer where you can have one or many orchestrators. And then we have a top layer with reducers. The idea of this is that the clients, they are data nodes in principle. Their role is to update and validate models. Orchestrators, they act as combiners. So an orchestrator is a stateless agent that combine model updates from k different clients into a single model. This model is then forwarded to the reducer, and the reducer's role is to take models from a number of different orchestrators and then aggregate them or combine them in different ways and make them ready for prediction. The nice thing with this general model is that using it, you are able to create quite a few different types of implementations of federated learning. So if you think about it, federated averaging, the algorithm that is most well known and that we discussed earlier in the talk, is just a special case of this pattern. So in this implementation, you have one orchestrator that conduct a number of rounds. In each round, you typically subsample a number of the clients. This is largely due to scalability issues that you cannot practically handle too large number of clients in a single round. For us, that means that we can forward the model from that orchestrator up to the reducer. So this is essentially the identity map. In this case, the reducer doesn't really do anything. But with this kind of the general case, you obtain federated averaging. Coming back to this model, you can make analogies, of course, with MapReduce here, where the role of orchestrators would be like a local combiner in that setting. So in this model, one way to scale federated averaging in a trivial way would be to simply add more orchestrators. So this slide illustrates that idea. By adding more orchestrators, you can, in parallel, so each orchestrator will do this independently, work on a subset of the clients and train its own federated model, typically with federated averaging. We can then have the reducer on the top level then reduce these models, again averaging the weights, into a global model. So mathematically, I mean, this will amount to the same result as doing it with one orchestrator, but in this case, what we have gained is increased scalability and parallelism. And when I say in principle it will do the same type of averaging, I think it will, of course, affect convergence rate and so forth if you compare a sequential rounds versus parallel rounds. But this is an illustration of sort of how we think that our general model enables high scalability. But we can also leverage this model to do different types of models. So this picture illustrates how we can implement meta models using the framework. So as in the previous slide, we can let each orchestrator work on a subset of clients. But now let that orchestrator train on those clients until convergence, each of them producing one shared model. You can then publish these to the reducer, and the reducer, instead of combining them with averaging, you can construct sort of voting or aggregate predictions in an ensemble model. So this picture here would be bagging federated averaging. And this, of course, can have also benefits like bagging has for normal machine learning. I mean, variance, reduced variance, for example. Another very interesting aspect of this model that you see here is that it also allows you to purge individual member contributions from the global model. As illustrated in this picture, say that I have one client in the alliance that for some reason we would like to remove all contributions that that client has made. So with traditional federated averaging, this would be probably an impossible problem, or at least very, very hard. With this type of ensemble model, it's quite easy. So in order to remove contributions by that client, you just have to track all the models on the orchestrator level that client has been involved in, and then simply purge them or delete them on the reducer level from the ensemble. This can be a huge benefit in the situation where you need this feature for alliance governance, because it would be a massive cost for a long-running alliance if you had to go and retrain the model from scratch if this situation arises. So the model that we propose for FEDn allows you to construct these type of ensembles or meta models quite naturally, and they can have this additional benefit then that it's possible to remove or purge contributions from the alliance. Now, the motivation for thinking about federated learning implementations and algorithms in this way is not just to have a flexible interface for implementing different types of algorithms. I mean, that is important, scalability is important, but perhaps even more importantly, we think, is that this situation arises naturally in many situations. I mean, one good example is the fog edge scenarios. In this case, clients correspond to edge nodes. Orchestrators in this setting can be deployed and correspond to fog nodes. It's possible that you would like to have a sort of nested model that incorporates information that is unique to each layer in this network. So, for example, clients or edge nodes might have one type of data set, train a model based on that, which orchestrator then combine into one model on the fog level. But it's conceivable that you could then use this model in combinations with other data available on that layer of the physical system, and so forth, in order to combine them then and produce another model on the reducer level. And we think it's possible, of course, to generalize this general computational model to an n-tier system if motivated by that situation. Up to now, we have only talked about the training of the model and constructing the model in the first place. Validation of the model is an equally important part of the federated training procedure. And here we just note that validation can, of course, be done on all levels or tiers. I mean, typically, we work with different situations. Maybe a client, each client has set aside a small tester validation set. Definitely they have their training data. It's conceivable that orchestrators have some sort of shared data set aside for testing, and correspondingly on the global or top level, there might also be test data. In the FEDn implementation, each client natively runs a validation service. So as an orchestrator, you can ask a number of clients to provide a validation or scoring of that model according to the code that you provide. But you can also implement, and as I said, validation steps on the different tiers. This problem of validation is interesting and is tightly related to sort of the general problem of alliance governance. What you see here is an example of a training scenario. You see the output of one orchestrator's combined model. Here each client that this orchestrator talks to is running a validation service. In this case, it's training on the MNIST dataset, classical CNN. And the picture you see here is a snapshot from the FEDn dashboard. And this kind of illustrates a quite important question or problem for practical machine learning alliances. I mean, what constitutes acceptable model improvement? Is it a mean improvement, a median, the best or the worst? Should it be done with local or shared validation data? What is the truth and what is available? The answer to this question, I guess, is both a matter of the business part of the alliance governance and the machine learning part of the problem, which makes this a quite interesting problem. Another very important practical aspect of designing and building a federated learning system like FEDn is that of monitoring, checkpointing, and provenance tracking. So here we can sort of distinguish between two main scenarios, one where you have a trusted third-party configuration and one you have a fully decentralized system, trustless system. So if you look at the third-party configuration scenario, we want to have we may want to have extensive tracing of alliance messages. We want to be able to track pretty much all the steps that has been taken in the coordination of creating this model. This in order to be able to recreate the timeline of model construction, to look at what happens, what has happened historically in order to do root cause analysis and so forth. I mean, this requirement is really not different from any other enterprise grade system where you need to be accountable for the construction of the state of the system in the end. In our solution, we have a pretty scalable enterprise backend for monitoring. It's based on gRPC and MongoDB. This is really the data lake situation, so other solutions here are also possible, but this works well for us so far. It's important, and this is also part of the alliance governance process, it's important to agree on an alliance what level of information is to be logged and stored. It's not obvious how you would do it in a particular setting, but it's possible, it's at least conceivable that this type of data could be very useful as augmented data or auxiliary data when trying to do, say, inference attacks when you have access to the model endpoint. Although how you would actually do this in practice is in fact a very hard problem in itself. So in addition to this more traditional monitoring system, it's also possible to leverage blockchain technology to create immutable audit trails and to track model provenance. So this is a topic, this is something we're actively working on, and it's the sort of central topic of one of our R&D projects that we're running in the Scaleout team, funded by the Swedish innovation agency Vinnova. So I'd like to summarize my talk with a few key takeaway messages. And the first one is that federated learning or FedML model construction is not a one-size-fits-all type of problem. We believe it's important in our implementation to allow for flexibility, both with respect to the model framework that we use, but also how we implement algorithms and also on the deployment side, how can we deploy our framework in different levels and different tiers. Here we find that a well-defined computational model helps a lot when we're trying to think about mapping different use cases and different use case domains to suitable runtime implementations. That kind of simple model that we propose with FEDn is an abstraction based on clients, orchestrators, and reducers. Clients, they are data nodes, they update and validate models. Orchestrators are combiners that aggregate models from a number of different clients. And then reducers is a top-level agent that combines models from orchestrators into an overall global model. I told you in this talk that with this simple model we can construct algorithms from vanilla federated averaging to hierarchical federated averaging to meta models, ensemble models. I also sort of proposed that this type of tiered model can be very useful when you think about, say, fog and edge scenarios. And finally, federated learning or FedML model training is one of many important aspects of the problem. So model validation, monitoring, provenance tracking, incentive design, model access and distributions, they are also part of the general problem of alliance governance. So this is a wider problem than training the model. And one question that I'd like to raise, I mean, is there such a thing as FedMLOps? Or is this just the same or an application of MLOps? Are there additional complications and challenges to address? So one immediate thing that comes to my mind there is model serving, which could be complicated by privacy concerns or availability concerns of different agents in the system. I just want to wrap up with saying that the way we attack this more holistic problem of alliance governance is through synergistic effects between FEDn and StackN. So StackN is another open source project that we're working on, an end-to-end framework for machine learning, model development, lifecycle management, and resource management. So together these two open source softwares become sort of an end-to-end decentralized AI solution. With this, I would like to thank you for listening, and I'd also like to thank the entire Scaleout team for working hard every day to sort of make our visions for production-grade federated learning come to life. So thank you.